Good afternoon. Is somebody only English speaking at the audience? All right, so we go in English. I am Lieutenant Commander Mpalagiannis, and with our colleagues Tsamopoulos, Kalogrias, and Professors Tsekouras and Kanellos, we will try to answer the dilemma. We will try to answer the dilemma: application of photovoltaics on ships, on the power system, electrical power system. This is a reality or a utopia? There's a lot of talking about the need for reduction at the greenhouse emissions. The marine systems contribute to that, and in order to achieve the goals, there's a tendency to go to the all-electric ship. And we need more electricity on board, and we want that electricity to be green. So the solar photovoltaic technology is already relatively mature, but in inland applications. The research that has been conducted has led to this experimental trimaran to Ranor. It has completed the tour of the world. It has great performances. It's a trimaran of 35 meters long, and it has a photovoltaic surface of 512 square meters, an autonomy of 72 hours, and a maximum speed of 14 knots. Of course, in this example, in this construction, there is a lot of thinking about the cost, because it is a technology exhibition vessel. Let's start from what is a photovoltaic cell. We can see some layers of semiconducting material here. On top there is a protective glass for the weather conditions. Then it is an anti-reflective coating, the yellow layer. We have the two black contacts, and between there is the semiconducting material, silicon, the N-type, the P-type layer, and between the PN junction. At the bottom there is a protective insulation, and when sunlight strikes on this material, we have the photovoltaic effect. That means that an electric field is produced between these layers, and we have movement of electrons, electricity. There are different kinds of solar cells, and we think that the two with the monocrystalline and polycrystalline solar cells are more suitable for marine use, because they have good efficiency, they have good expected lifetime, and on board the ship the space is valuable. So we need good efficiency and good energy density. Some characteristics of the photovoltaic cells is the production of direct current, DC. That means that in some applications it has to be transformed to AC. The photovoltaic cell is a low voltage and high current device. Its power density is the inverse of the equivalent of the surface that is needed in order to produce from solar light 1 kilowatt. and the modules are classified according to the supply voltage output, 12, 14, 36, 48. We use this electricity to serve common electrical loads on board. That means it could be ventilation, wireless, lighting, and this is why we need more voltage. So we have to interconnect the cells, the solar cells, in panels, and the panels are connected in series to form strings of panels. The current is the same on each string, and the strings are connected in parallel to form arrays. There are some diodes to protect the arrays from variation of voltages. But an old Chinese saying says that one photo is better than 1,000 words. So here we are. These are the cells. They form the panel. The panels connected in series form the strings, and each string connected with the other in parallel make a module. So in order to proceed to the application of photovoltaics in the energy power system of a vessel, of a marine vessel, we have to step on specific technical topics. The electrical power system, which are the marine environment conditions. It's a rough environment. Which will be the position, the place of the photovoltaics on board? What is the requirements for the attacking corrosion in the marine environment? What should be the technical strength of the panels? If there is any maintenance that should be conducted, and this must be taken into account. And of course, last but not least, the vessel stability, because a ship is a floating construction. Let's see one by one. With the green color, it's something that is most a kind of advantage, and with the orange color is something that we have some difficulties. So some difficulties. The main problem of the photovoltaic energy, photovoltaic produced energy, is that it is not easily controlled. It depends on the weather. If the day is sunny, we have a lot of energy. If the day is cloudy, we have problem. And this is the reason that the photovoltaic energy must be consumed instantly or should be stored in a system of energy storage. That's why a sophisticated electric power and load management system is the system that gives the solution. It means maybe the energy produced by the solar cells must be at the same time led to the same loads with the electric energy that is produced by classical systems, diesel generators, for example. The marine environment conditions are rough. It is installed outdoor. We have wind salt, moisture. The exploitation of the sun energy is partial because the ship moves. Of course, we have an ease when we place the panels on the roof of the boat, and we place them horizontally in order to increase the solar energy absorption surface. But it has to be at least IP55. This is a standardization for electric systems in comparison with the moisture resistance, and it's preferably to be IP67. That means no moisture goes in. The position of the photovoltaic plant must be horizontal in roof facades of the superstructure or glass fronts. We have to avoid machinery spaces and funnels because there is oil, smoke, dust, pollution, and the inclined spaces, the inclined surfaces are giving shading problems. The same problem we have with antennas and radar masts and so on. They produce shading problems. The marine environment is very corrosive. So, there must be, I'm sorry about that, there must be a weatherproofing heat strengthening safety glass with protection maybe in hail. There must be a protection of the moisture for the electric junction and cabling systems, IP55 or IP67 that was mentioned previously. But the rest, the metallic parts, could be covered with a common marine coating, or could be galvanized, which is more expensive, of course. But also the use of aluminum alloys, it's something very usual nowadays in marine constructions. And it doesn't cost a lot, the use of marine alloys. What are the requirements for the mechanical endurance of these structures? The panels must withstand vibrations due to wave impact on the hull, bottom slamming, sagging and hogging, the motions when the ship is on the crest of the waves, deck wetting, sudden wind gusts, and multi-directional forces because the ship moves in all the three directions. Here you see a lot of green, so we have more advantages. Let's say at the beginning that it is almost a maintenance-free installation because there are no moving parts, no need for experienced personnel, no need for technical support, special tools, etc. The common electrical maintenance that is conducted for the rest of the electric power system of the boat is conducted for the system of the PV panels, and there is only exception for the energy storage system if it is required one. And we come to the marine vessel stability. The approximate weight of a panel we have thought that a panel of 1 meter in width and 1.98 meters long is suitable. The weight is 20 to 25 kilos per square meter. So we have some extra weight placed high on the vessel. But this weight is relatively low and can be compensated with the ballast tanks. Or we can use the storage energy system as ballast. Lead-acid batteries, for example. Of course, the weight that is placed high is reducing the riding arm. The riding arm is the momentum, the tendency of the ship to come to the steady position. And for the techno-economic estimations, we must say some things about we estimated the electrical power consumption of the vessel with the classical power system with diesel generators. We estimated the available area that can be fitted with photovoltaic panels. What amount of energy can be produced from the solar energy. We had a lot of discussion about the energy storage systems, and we had two choices. The cost with or without the energy storage system, a lot of discussion, as I said you before, and we made a comparison of different solutions, and there is a diagram about that. For the case study, we choose a catamaran. Why? Because it provides a lot of surface to place solar panels, and as you can see here, this is a catamaran and this is a monohull. This is the riding arm of a catamaran, and this is the riding arm of a monohull. That means that even though that you place weight on top of the catamaran, the possibility of capsizing is almost zero. That's why we choose a catamaran. Our boat, a passenger ferry, 120 passengers and plus 10 crew. The available surface for photovoltaics is 358 square meters. For the propulsion, the power is 250 horsepower, but we don't care about that. We care about the the energy consumption, which in the classical scenario is generated by two diesel generators with a total power of 202 horsepower. 35 meters length overall, 32 meters the length of the superstructure. There is here a bridge 2 meters width that produces some shading problems, but that's not a lot. And the basic scenario with no photovoltaic installation is an electric system that serves the ventilation, the air conditioning, auxiliary machinery, water pumps. This is serviced by two diesel generators of 202 horsepower, and we have taken as granted that the use of the boat will be 10 days, 10 hours per day, for 5 days per week. This is for all the three scenarios. And the total fuel consumption per year for this classical solution is 9,700 721 liters per year, just for energy production, for energy generation. So the first scenario is placing 100 photovoltaic panels with an energy production of 25 kilowatts. The area is 165 square meters. We thought that a corridor of 60 centimeters dividing each string is suitable for inspection and maintenance. And the results is that from April, May, September, and October, the energy production from the photovoltaic system overlaps the consumption that the electrical system needs for the electric loads, ventilation, auxiliary, etc. The energy surplus goes to a battery storage system, and the total fuel consumption is about the half than we saw in the classical solution, 4,480 liters per year. The more optimistic scenario is placing 198 photovoltaic panels, no corridors between. We have 18 strings with 11 panels every string, and all months except February, January, February, November, and December, and we will show you an image with the solar peak afterwards. All months except January, February, November, and December are covered by the energy production of the photovoltaic system. The energy surplus goes also to a lead-acid battery system, and the total consumption is just 1,632 liters of fuel oil per year. So this is the image I was talking about. This is the basic scenario with the two diesel generators. This is the scenario with the 100 panels, and this is the scenario with 198 panels. And you can make out that the solar energy peak is from April until September. Here's a comparison of the two scenarios with the basic parameters, the fuel cost and the discount rate. And if the fuel oil cost is above each these two lines, each one is for the second scenario and the first scenario, the use of photovoltaics is profitable. So, in the 2 minutes that are left, I want to remind some milestones. There must be the necessary area available, so we need a wide boat. There must be the adequate marine and technical specification, because the marine environment is a difficult environment. IP55 strength, resistance. The energy management system for partial or surpassed energy production is the one that gives the solution what to do with the rest of the energy or with the lack of the energy produced from the photovoltaic systems. And of course, the fuel oil cost and the discount rate of the capital investment are the two parameters that show if it is cost effective or not. Our answer to the dilemma is that application of photovoltaics on board is a reality. And I want to close with this photo, which is taken in a shipyard nearby. Thank you for your attention, and I'm looking forward for questions.
5 minutes again for questions. Yes, I have a short question. The first one refers to the analysis that you have done. Did you take into account the increase in weight, the mathematical cost, for example? The catamaran that you showed the 2 runs, that weighs 90 tons. Batteries, it's 509 tons, just the batteries, but include the rest of the power generation equipment. Yes. This means that for a small vessel, increasing the weight significantly to give you an extra draft, which means you need more power to move the ship at the same speed. So you do this trade-off analysis.
We didn't analyze that in detail, but the whole additional weight was approximately 6 tons. It is not very much for such a kind of vessel, and of course you will have some decrease in the maximum speed, but it was not, sorry, it was not very much. So it was inside the limits that we had set.
My second question refers to naval vessels. Do you believe that for naval solar vessels, is it something feasible? Naval vessels?
On naval vessels, we have other requirements. We have the U.S. Navy says that the naval vessel is a vessel that can float, can move through the water, and can fight. So, the third, according to the U.S. Navy, the third requirement cannot be fulfilled in a ship which is covered with photovoltaic panels. Maybe for auxiliary vessels. I mean, I remember in the Salamis Naval Base we have personnel transport vessels. That's a good field for application, I think. But naval vessels that are going to battle, I think it's not feasible yet.
Maybe to want to his remark question, maybe a partial use of photovoltaic panels for energy would be used in naval vessels. Partial use of energy, not the full energy demand.
Of course, the all-electric ship that I mentioned at the beginning is it's maybe far away. Of course, there will be such an application will cover a part of the all the energy production, but for naval vessels that can be submitted to strikes, I think it's not under consideration at the moment. It must. We should have very resistant panels, which is not feasible at the moment. Of course, yes. There are also other requirements that radar cross-section that must be minimized on a combat vessel. So you have difficult geometry in naval vessels, while in auxiliary and transport vessels you don't have these restrictions.
Thank you. You can ask another question of the lake. If you jump the possibility of pulling the panels
Yes, this is, in our opinion, not a good option, because we will produce brine residuals, and that will decrease the efficiency. So the horizontal placement of the panels is, can we go, please, Dimitri, μπορούμε να πάμε πιο πίσω. Here we are. Horizontally placement of the panels will increase the solar energy absorption surface and will reduce the panel cooling. So they become more efficient with this kind of geometrical arrangement. But placing an extra cooling system will reduce more the efficiency. And of course, seawater is not a good friend of electrical parts.
Thank you.
Thank you very much.